Okay, now we're going to look at how banked curves can be used to supply a centripetal force. And for this one, I'm going to assume that there is absolutely no friction. All right, so if a car is going around a sharp corner, there needs to be friction. But if the car is going really fast, banking that curve helps supply the centripetal force. So this is supposed to be a car, the front side of a car it's coming out of the board towards you. Now let's look at the forces acting on that car. You've got a gravitational force, and you've got a normal force, perpendicular to the track. Now, we're kind of used to situations like this. If this car were going up an incline, the size of the normal force would be smaller than the gravitational force. In this case, though, however, the size of the normal force is larger than the gravitational force. And that's because, if you think about this car is moving into the track. Its natural tendency is to keep moving out, tangent to the curve. The track is getting in the way. So this normal force has a size larger than the gravitational force. Now, maybe I'm going to draw this a little bit bigger so I can do this and you can see it. All right, so I've got a gravitational force down, I've got a normal force perpendicular to the track. Since there's no friction, there's no other forces acting on this car. So this means that since the car is not accelerating up or down, the component of the normal force in the vertical direction is the same size as the weight. There's also an x component to the normal force. This x component is the centripetal force. All right? If there's no friction up the ramp, this is the only horizontal force toward the center of the curve. So I've set that equal to mv squared over r. Now, let's think about this a little bit. If this is banked to an angle of theta, so if I start out horizontal, the normal force is perfectly vertical. The more I tilt that surface, the more the normal force gets tilted. This is also theta. All right, so let's put n here. Now, if I do a little trig, the tan of theta is opposite over adjacent. So this horizontal component of the normal force is mg tan theta. So that means that mv squared over r is equal to mg tan theta. All right, so if I continue this on, you see the mass has absolutely nothing to do with it. So I'm just going to solve this for v. So this would give you the maximum speed that you could travel and still navigate this curve for that theta.